Let's begin. Welcome again. I hope you had a good weekend. First note about student groups. I sent an announcement asking you to email me your student group names. Please do that by Thursday. Like today, you're here together. Maybe take a moment after class to come up with a funny name. I already had a couple of groups send their name suggestions. We will print those out for you. Maybe laminate them even so they are more official and formal, and you'll put them up here. I'm really jealous of these red, tabs here. Anyway, so we'll do that. If you don't send a group name, your name will be anonymous. We'll index you from 0, anonymous 0, anonymous 1, and so on. So I'll make a few of those. So we had 12 groups. So I'd appreciate it if you send your group names and the group members by Canvas email to me, please. We will continue on error analysis, our error discussion today. We'll wrap it up. We have a really cool exercise in Python to demonstrate how the Taylor series works visually. We'll do it together. And we'll wrap up the subject on error analysis, take a break, and hit Unit 1 of this course, which is solving algebraic equations. If you recall, last time we left off discussing the types of errors. We had round-off error. We gave a few examples on your homework assignment. The Scud missile round-off error disaster, you solved that in your homework. The other error we're concerned with in numerical methods is truncation error. Truncation error, as we define it in engineering and mathematics, has to do with truncating an exact mathematical series, an exact mathematical formula into a subset of that formula. The greatest example of that is the Taylor series. It has an infinite number of terms. We choose to only use a few of those terms. The remainder is going to be the truncation error. Okay? Again, remember in computer science, sometimes they refer to round-off error or truncating a number that doesn't fit. Let's say you have a 32-bit precision number that you're trying to fit on a 16-bit register. Whatever doesn't fit, they call that the truncation error. It's technically truncation, but to us, we call it round-off. Okay, just a matter of definitions. Okay. So I'll remind you again of the Taylor series theorem, and I'm assuming you saw that through calculus. We're going to see another form that you might not have seen through calculus. But the way I like to think about the Taylor series, one way to think about it is to say, if you have information about a function, its first derivative, its second derivative, and so on, at some point A, then you can estimate, if you only know those pieces of information, you can estimate that function, the value of that function, at some other point x that is x minus a away from a. Okay? So this is the statement of the theorem, is that the value of the function at this new point x is based on the value of the function at a, its derivative at a, its second derivative, and so on. All right? This is an exact mathematical expression. Those equal signs are equal. You're assuming you're taking this to infinity. Okay? And the way we say this, we say that this is the Taylor series of f of x around point A or in the vicinity of A. Okay? Now, this A doesn't have to be equal to 0. It could be any point that you choose. And clearly, if you're trying to approximate or estimate a function around some point that's not 0, classically we're used to using A as 0, like the Taylor series we did for sine and the exponential. But A could be really any point. So your exercise now, your activity as a group, is to write the Taylor series of the exponential function. So now you know the exact function e to the x, okay, in the vicinity of a equal 1. Now, I know you know f of x, and you're going to be like, why are you doing the Taylor series of e to the x? Where you'll see once we start doing finite differences and differential equations, you'll see the usefulness of that, because we will not know what the actual function is. But for the sake of the argument, just take f of x, so you know the derivatives. The derivative of e to the x is e to the x, right? So try to build the Taylor series, write 2 to 3 terms of it, around the point a equal 1. Okay, so here's the statement. Write the Taylor series of e to the x in the vicinity of a equal 1. Write 2 to 3 terms out of it. Okay, work as a group. Come on. Go humming and buzzing. I want to hear voices and talking and loudness. One of you could write, the other could hypothesize and theorize. Write it by hand or type it. Just express it analytically, okay? I want the formula for e to the x in the vicinity of a equal 1. The first, second, third derivatives of the exponential function are e to the x. Write out the first few terms. Remember, x has not been specified yet, right? So x is our unknown. But we know x is going to be close to 1. That's why we're developing the Taylor series in the vicinity of a equal 1. But we haven't specified x, and that's the point of it. Because I want to use this formula, let's say, in a calculator to evaluate e to the 1.1, right? So I develop the Taylor series in the vicinity of 1, okay? Just write out the first few terms. The first term is e to the 1, right? Okay. If you have not formed into a group yet, please self-select. If half of your group is missing, just feel free to barge into another group. Please allow others to join your group if their group is missing. You can be loud. It's allowed. That actually rhymes. You can be loud. It's allowed. Yeah, just write out the first few terms, 2 to 3 terms. Keep it analytical. No need to compute anything. Okay. Let's see, do we have any answers? First term is e to the 1. Second term, e to the 1, x minus 1, because f prime is e to the x. F prime at a is e to the 1, right? Times x minus 1. What about the third term? Okay. Anybody disagrees with that? And so on. Right, I'll give you my answer. So in the vicinity of a equal 1, e to the x is e to the 1 plus e to the 1 times x minus 1 plus 1 over 2 factorial e to the 1 x minus 1 squared, and so on. All I did was substitute the value of a and evaluate the derivative, second derivative, third derivative, and so on at all of those points. Okay. But it's still, this Taylor series is a mystery, right? Because it's like, it's so powerful, and we saw the example of how we can use it as a calculator to evaluate functions that we don't know how to compute. But also there's a way to visualize this idea of in the vicinity of. So what would be cool is if we take the Taylor series of some function, take that function, assume we can plot it exactly for all values of x, and then write the Taylor series of that function around some point and start plotting the first term, then the first 2 terms, then the first 3 terms, then the first 4 terms, and so on, and see how adding more and more terms, try to see visually how well they're going to approximate the function, because that's the claim in the end. The Taylor series, in its glory and all of its infinite terms, is an exact answer to the function. But if we truncate it, it's going to be an approximation. So how well does this approximation look like? We can visualize it. So here's our coding activity. Grab your Jupyter notebooks. We will work on this together. The purpose of this coding activity is to visualize the Taylor series and demonstrate that by adding more terms, we get closer and closer to the true answer. For the function f of x equals sine x in the vicinity of a equals 0, so right around the origin, okay, we will plot 1, 2, 3, and 4 terms in the Taylor series expression. Okay, so the Taylor series for the sine of x around a equals 0 is this formula, x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on. This is what the calculator uses to evaluate the sine function. Okay, like we did last time, it keeps evaluating terms until it hits a certain relative error, relative tolerance. And then plot on the interval minus 2 to 3 or minus 10 to 10. We can change that. So here's my solution strategy. Very simple, straightforward. On the same graph, I'm going to plot the first term. So f of x equal x. That's going to be a straight line. Clearly, that's not an approximation to sine x, but you'll see it intersects sine x right around the origin. Then the next approximation is going to be the first 2 terms, x minus x cubed over 3 factorial. That's a cubic, right? And then the third approximation is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. That's a polynomial of order 5. And we'll see how those curves look like compared to the true function sine x, which we will also plot. All right? So let's do this. Grab your Jupyter notebooks. I will create a new notebook. And I assume you've done some plotting in 1703. If you haven't taken 1703 or stats, we'll work through this together, show you a few tricks. And we see in the back? Okay. So boilerplate, NumPy. Import NumPy as MP. Let me zoom in a little bit more. Okay, this is better. All right? And then for plotting, there's a library called matplotlib, if you're not familiar with that. In matplotlib, there's Python plot, which is our plotting utility. So if you don't remember this, just memorize this. Import matplotlib.pyplot as PLT. So I'm going to give it a nickname, PLT, for the plotting library. Okay? How many of you have done this before? Awesome. Okay. Have you done linspaces to plot functions? Great. Okay. All right. I will also need the factorial function, and that lives in the math library. So I will import math. And I'm not going to give it a nickname because I love the word math. Okay, so I'm going to, what nickname would you give math? Myth? MTA? I don't know, right? So I'll just keep it as math. Everything from math. All right. So the first thing when you're thinking about plotting, especially just a one-dimensional function, is that you have y values and x values. So you need to define what your x values are. Okay, so I said in the coding activity, plot it from -2 to 5 to 3. Let's say we want to plot it from -10 to 10, just kind of for the sake of it. We'll see how it looks like, and then we can adjust that interval. The fastest way to generate points on that interval, because you need to generate, because you're working programming, you need to generate a sequence of discrete points on that interval, -10, -9.5, -9, and so on, right? You need to generate a sequence of points, equally spaced, unequally spaced, doesn't matter. And then you're going to take that function, evaluate it of those points and plot those values, right? That's what you're effectively doing when you're plotting. So the fastest way to generate a sequence of points is from the NumPy linspace library. So I'm going to call this, let me do this. NP, if you call linspace, okay, if you call the function linspace, you open the parentheses. Now, what the heck is linspace? What if you forget what linspace is? Here's a little trick. You open your parentheses, okay, put your cursor inside and press Shift-Tab. If you press Shift-Tab, it gives you what we call the function API, or the, I'm like, wow, why didn't anyone tell us about this, or whatever. This is the function signature, or this is how to use a function. If you forget what argument a function takes, and you don't want to go on Google or GPT, whatever, right? You can press Shift-Tab, and it gives you the function signature. So what this tells me here, and you can go in and scroll. Hold on. Sorry, all right. So if you press Shift-Tab twice if you want, it expands this full function signature, okay? And it tells you, oh, there's the first argument is start, the second argument is stop. Okay, hold on, some reason it's not allowing me. Okay. Sorry, my Python looks like it's a little messed up. Okay, there you go. Right. And it explains what the function does. Oh, linspace returns evenly spaced numbers over a specified interval. That's great. This is exactly what we want, right? And all I need is the start and stop. Num, what is num? If I scroll down a little bit, it explains everything. Parameters, start, the starting value of the sequence. Stop, the end value of the sequence, okay? And unless endpoint is set to false, in that case, then it includes the endpoint, okay? Num is an integer, optional integer. It's the number of points you want to generate. By default, it's 50. But what if I want to put 100 points between minus 10 and 10? Or 200 points between minus 10 and 10? Okay, change that number. All right? Now, everything else, I don't think I need to change. I can leave it to their default, whatever those mean. I'm not going to touch those. So let's just try it out. I'm going to do linspace from minus 10 to 10. And if I just do this without anything, and I press Enter, oh, look at that. It creates a NumPy array with equally spaced points from minus 10 to 10, 50 points, 50 of those points, right? They're all equally spaced. I can do 10 points between minus 10 and 10. So they're going to be minus 10, minus 7.7. I can do, okay, so this is the num argument. I can do 100 points. Okay, here's 100 points between minus 10 and 10, and so on. So let's do it at 200 points so that it's really nice and clean when we plot the true function, sine of x, and all the other functions. And I'm going to store this array in a variable called xValues, or xvals. Okay? And if you're in doubt, print it out, print xvals. This is cleaner. Okay? There you go. Perfect. I'm going to comment this. Oh, how do you comment? Command / hits you with a comment. Okay? Command, or on your PCs, on the Windows, what is it? The Alt or something? On the Mac, it's command / okay? And you can, it's really cool, you can select a bunch of lines and comment all of them. If you press it again, it will uncomment it, okay? Okay, so now let's plot. We're ready to plot very immediately. Here's how you plot. PLT dot, what is the function for plot? Let's say you forgot. If you press PLT dot and press tab, it gives you all the functions that are available in that library. So take a library, PLT, put that dot, and then press tab. It gives you all the available functions that PLT provides, all right? So in this case, everything, because I typed P, PLT.P, is going to give me everything that starts with P. I want this one, plot, parentheses. Oh, what does plot take? Command Shift-Tab. and gives me the function signature. Oh, it plots x and y values. All right, so you can dig through this, plot x and y using line and style color. Perfect. So that's all I need. I'm going to plot x vals. What are my y values? Now remember, any NumPy function operating on an array is going to return an array. So if I apply sign x on x vals, it's going to return an array of sign values of each value of x, right? So I can do it in line. I can do np.sign of x vals. Now np.sign of x vals, if you don't believe it's an array, just copy it, go out, and print it out. Again, when in doubt, print it out. Look at that. Each entry contains the sign of the corresponding x value. Right? If we plot this, we get this. Okay? All right. All right. Here's where I'm going to lay some wisdom on you. You might have known that wisdom, which is great. But if not, this is a crappy plot. Can you tell the difference in quality between the text that you see up there and the pixelation going on here? You can tell the difference, right? Why is that one such nice, clean quality? If I can zoom in to infinity here, and it will still look nice and crisp, but this plot gets worse and worse. And if you go and print this one on a real size paper, it's gonna be this big for a reasonable quality. The reason is that by default, Python is gonna generate low quality plots that are called raster images, pixel-based images. But this is unacceptable in this day and age. I am creating these plots. I should be able to create vector-style graphics. Vector graphics, I like the font that you see up there. You can zoom into it to infinity, and it will redraw itself. So how do you do that in Python? There's a little trick in Jupyter Notebooks. You might have known this, and I hope they don't deprecate it yet. Okay? So right before you import matplotlib, add these two lines. Copy them, memorize them by heart. Okay? They exist in every notebook that I have my name on it. Okay? Because I refuse to see a low-quality plot. Okay? So first, you put this %sign. These are called magics for Jupyter Notebooks. Okay? And do matplotlib inline. You might have seen that. But this is the cool piece. Config, inline, backend. Don't ask me how I got this. I Googled a lot. Figure format equal SVG. Anyone know what SVG means? Scalable vector graphics. That's the foundation of vector graphics. Vector graphics, by definition, are graphics that redraw themselves as you zoom in. Okay? So you get infinite resolution. Here's what it looks like. Oh, matplotlib. Okay? Now look at this. If I zoom into this, it's beautiful. Look at that. So now imagine this plot with 50 curves on it. It's going to be the difference between light and day. Between night and day. Okay? That's my advice to you. Now, so this is purely visual. Now to export your plots, don't export them as JPEG or PNG. Those are raster. They're pixelated. Export them as PDF or SVGs. You will get impeccable quality. All right. Enough with that. OK, so now we have our sign function. Let's go ahead and plot the individual terms in the Taylor series. So first term, first two terms, for three terms. And let's see what happens. So I'm going to define those terms as functions, f1, f2, f3, okay, as routines. So I'm going to define def f1, that's the first term, okay, and I will return x, right? That was the first term, that was the first term in the sign function, right? Now, the first two terms I will put them in F2, and I will return x minus, it was x cubed over 3 factorial. So math.factorial 3. All right. Or if I don't want to write math.factorial 3, I could do from math import factorial. So I only import the factorial function from math. Okay, so when I come here, I don't have to type math.factorial. Either way, doesn't matter. Now let's do the third term. And again, all of these sequence of terms, they are like their individual functions. You can plot them versus x. Don't lose our objective. Our objective is to see how close these terms get to the true function of sine x, which is kind of oscillating and nice and sinusoidal down there. Okay? Well, the word sinusoidal comes from sine, right? Okay, so return. I'm going to return f2 of x, and then the next term, which is x to the power 5 over factorial 5. And let's add one more term, f4 of x. Oops. Return f3 of x, right? Because each term contains all the previous terms plus one additional term or minus one additional term. X to the 7 over factorial 7. Are we in agreement? If you already printed this out, go ahead and start plot f1 of x on top of the sine function. And then plot f2 of x on top of f1 and the sine function and see what happens. If you're still copying, I'll give you a minute. As you copy, here's a trick. Read it. You're copying, you're more likely to retain and understand if you're copying something if you read it. Okay, say, f1 of x, return x, I'm return, and try to process it a little bit. For some reason, Siri keeps turning on here. She likes my voice, apparently. Okay, great, good. Okay, so let's go ahead and plot plt.plot. I'm going to plot the first function, x vals, and I want to plot f1 of x vals, right? Whoa, So if we approximate the Taylor series of sine x with a single term in the vicinity of 0, if we approximate the Taylor series with the first term, x, clearly, just visually, it looks like a pretty good approximation around 0, right? That's the point 0. But as you go away from that point, a equals 0, you lose, you're far away, you depart from the true function. So let me clean this up a little bit. I will add a grid, plt.grid. Okay, so if we add a grid, it gives us a nice grid. And let's kind of home in here around the point 0. So if you do plt.xlim, and we'll do -1 to 1. Okay, oh, we're zoomed in between -1 and 1. Look at that. The orange line is the first term, and the blue line is the true function. We're like pretty darn close. Let's limit the y-axis as well to see better. Y limit. Let's go from -1.5 to 1.5. Okay, look at that. Right, near 0, near the origin where we expanded the Taylor series, the two are indistinguishable. The true sine x function and x are indistinguishable. If you remember in your calculus, in the limit of x approaching 0, the limit of sine x as x approaches 0 is x. That's it, because of this. The first term, x, near 0, is a very good approximation to the sine function. But as you go away, you start departing. Okay? So let's add one more term. Now I'm going to comment these limits so I can see the big picture. Let's do f2. Okay, so I can't see much, so I'm going to limit the y-axis a little bit. Minus 5 to 5. Oh, look at that. One more term, so two terms now in that green line. The blue is the true function. With two terms, we're able to go farther away from the central point around which we expanded the Taylor series, right? You can tell visually it takes us farther away, but then it departs. Okay, what do you think is going to happen if we add one more term? Just going to continue doing that same trend. And we're going to get closer and closer to the true function, right? So let's do F3. F3. The F3 gives us that red line. It took us slightly farther away from the green one, so 3 terms, but just ever so slightly, especially over here. Okay? And the pattern continues. You add, let's do F4. I mean, this becomes obvious, right? Do F4. F4 is this purple curve. So we started with the orange, green, red, purple. We're getting closer and closer to the true sine function everywhere. But in practice, you only worry about the vicinity, okay? So you can get away with a few terms in the vicinity. But if you depart away, you will need more and more and more and more terms, right? You'll need more and more terms. So that's, for example, you can test this out on our algorithm we used last time. Do the Taylor series for the sine function, and you will see that if you evaluate the sine of 0.01, you'll probably get the answer within 2 terms. But if you want to evaluate sine 1 using the expansion around 0, you'll probably need 10 terms, okay, just to get to that value. So this explains, how the Taylor series operates. Each one of those terms successively improves our approximation of the sine function. Okay? All right. Let's get back to our slides. Okay. Now, the truncation error, like I said, you cannot add an infinite number of terms. The term at which you truncate, sorry, there's a typo here. You truncate. The term at which you truncate defines your approximation, and the rest defines your truncation error. So suppose you truncate at any one of those points over there. This would be your approximation, and this would be your truncation error. Kind of obvious. Whatever you leave off is a truncation error. And for the case of the Taylor series, you know exactly the expression of that truncation error. Okay? It's still an infinite number of terms. And so if you truncate at term n, the truncation error will be in general for any function, 1 over n factorial, f to the nth derivative at a times x minus a to the power n, plus a bunch of other terms. Right? Now, it's still an infinite number of terms. Now, luckily, there's some math theorem that says this entire truncation error, which is a summation of an infinite number of terms, is bounded. What do we mean bounded? It doesn't go above a specific value. This is one of the fundamental theorems of calculus, and it says that this entire bound is bounded by the leading order term. It has to do with the mean value theorem, okay? By the leading order term, so which is 1 over n factorial, nth derivative, but instead of a, it's some point between x and a. Okay? Now, what you take out of this is that this entire truncation error is bounded by this value. And this nth derivative at this point c, whatever this point is, don't worry about it. This value is fixed. For a given function, this value is fixed. Doesn't change. What is going to change is x minus a to the power n, how many terms you add. Okay? So here's how, okay. Now here's another way how we can write the Taylor series. And again, I'm trying to inoculate some ideas of the Taylor series because we will need them later when we get to differential equations. and when we get to finite difference analysis and Newton's method, the form that you saw is useful, but another form that is more useful for differential analysis is this form. Instead of putting A on the right-hand side, I'm going to take kind of A and put it on the left and say the expansion of f of x in the vicinity of x at some point h away from x, so f of x plus h, this is frankly easier for me to remember. It's f of x plus h f prime plus h squared over 2 f double prime plus h cubed over 3 factorial f triple prime and so on. It's the same formula you saw before, just written in a different way. You can take the previous formula and call A x and x, call it x plus h, and you'll get this answer. Okay, it's the same thing, but just different naming. But this is more useful for differential equations. You will see that by the end of the semester. And it holds the same meaning. Any continuous function can be expressed as a polynomial in the vicinity of h at an arbitrary point x. Okay? Okay, like I said, this form will be useful in building what we call finite difference approximations. So now, here's what you're going to do. Yes?
So I'm a little confused. Why would we use this, like the vicinity one, instead of just using like the power series? Like when we did e to the x, why would we do the vicinity to do 1.1 instead of just using it?
You're right. So in that case, when you're using the Taylor series as a calculator, you just do it around the value where you don't have the complex function, because we really don't know even how to evaluate e to the power 1, right? So you do it around 0, because in that case, e to the power 0 is 1, right? Or for sine x, sine 0 is 0, right? So for that case, that's true. But the reason I asked you to do that is because of this, because in finite difference methods, or ODEs, we actually don't know what the function is. All we know is that we have function values next to each other at a distance h. So what we're going to do, we're going to evaluate them relative to each other at some spacing h, and then our objective is to find f and f prime and f double prime. So we invert the problem. So that's the powerful use of Taylor series. We'll see that as we get to the end. But here's just to whet your beak, try to work out this problem. Now, using the Taylor series of f of x plus h, derive the forward Euler formula. Okay, so take that series out there. From it, give me an approximation for f prime of x, this approximation, and identify the truncation error. Do exact math. So take that formula, pull out f prime to the left, move everything to the right. So let me show you my solution. This formula, this forward Euler formula for rise over run, it comes from the Taylor series. Okay? Here's how I do it. Then isolate f prime. I take h f prime of x, move it to the left, and take f of x plus h and move it to the right. There's a negative sign, so I'll multiply by a negative sign. I get h f prime equal f of x plus h minus all of these terms. Now you see f of x plus h minus f of x, it emerges. Okay, what is f prime? I divide by h. That's it. That's all there is. This is the true full formula of a derivative. Now, we're not going to use that. We're going to approximate the derivative. This is really cool, because if I only know function values separated by h, this could be discrete data. You don't know what the function is or its derivatives. You just know the value at x plus h and at x. You take the difference, divide by the spacing. It gives you an approximation to the derivative, right? So that's how we use this x plus h in the vicinity of h, right? Now, we neglect all of those terms. Those are our truncation error. Why are we doing numerical methods, right? As long as you can quantify that error, it's okay. It's legal. Nobody's going to put you in jail for it, okay? So you can do it. It's okay. Yeah, make that jump in your mind. It doesn't have to be exact. It is actually exact math up till now. There's an exact equal sign. Okay? This is our approximation. This is our truncation error. Now, if you remember the rule for bounding, all of this truncation error, which has an infinite number of terms, is bounded from the top, from above, by 1 over 2h times f double prime at some value. Okay? Now, this f double prime of c is a fixed value. So here's the next activity we'll do together. What happens to the truncation error? So now this is our truncation error, this one. What happens to the truncation error as h is decreased? So if f double prime, okay, it gets smaller, but how fast? So if I cut h by half, what happens to the error? Cuts by half. Why? Because f double prime of c is a constant for that function. So if you cut h by half, the truncation error is going to be cut by h over 2, right? If you cut it by a factor of 4, it's going to be cut by 4, right? And that's what matters in that knowledge of, we don't know the true truncation error, but we know how it behaves, okay? So here's my answer to that, is that as the spacing h is decreased, so does the truncation error, because f double prime of c is bounded. That is, f double prime of c is some constant m, so that the truncation error looks like 1 over 2 m times h. And if you, as you decrease h, the truncation error decreases, and it converges to 0. So it's a consistent method. It's going to give you the right answer. And more importantly, from like my perspective as a computational person, the error is cut in half if I cut my spacing in half. So if I'm collecting data and I'm using forward Euler method, if I double space my sampling and I'm computing a derivative, for example, I'm only going to cut my error by half, which is not that exciting, frankly. There are more superior methods to this that you could cut the error by a factor of 4 or a factor of 8. Okay? We'll learn that when we do finite difference derivatives. Okay, so now I want to take this statement for the function f of x equal x squared minus 3x plus 1. And again, now we're using these toy problems to validate our discussions. Okay? I'm using these toy problems where I have an exact answer, okay, just to validate what we just talked about, that the error indeed decreases as we decrease h, and it gets cut by half every time we cut h by half. Okay? But there's a little gem in this problem. Let's see. For the function x squared minus 3x plus 1, compute the first derivative approximation using the forward Euler formula, fx plus h minus f of x over h, at x equals 0.5. Now h is an arbitrary value. We know as h approaches 0, the truncation error approaches 0. But I want to demonstrate that. I want to demonstrate that the truncation error indeed decreases consistently. So we will test this derivative for h values 0.1, 10 to the minus 2, 10 to the minus 4, etc. We did that in the last one of the problems. But in this case, we're going to report the absolute true error, because we know the true value. This is a toy problem, verification. We're doing verification. I know the true value. So we will take the true value of the derivative, this x squared minus 3x plus 1, and compare it with the approximate value that we computed at different h values. And then I'm going to plot those errors. I know it seems a lot, but frankly, like the best thing you could do with data is to visualize it, because it is worth 1,000 words. One plot is worth 1,000 words, okay? All right, let's do this together. I have the code for you here in the slides, but let's kind of build this together. Again, new notebook, please. And I will do my boilerplate stuff. And don't be like me here, Untitled 2, Untitled 7, Untitled 5. Name your notebooks correctly. All my notebooks are named correctly on my end, but these ones in class illustration, I'm going to waste time kind of typing the names, etc., because I want to work on the examples themselves. And create a new notebook. Okay. Let's import the boilerplate. What is the boilerplate? Just grab an old notebook, copy, paste. Okay. And copy this and paste it over here. I don't need math factorial anymore. Okay. That's what we got. All right. So first, let's define a routine for the function. Define my function. And that will return the x squared, that polynomial, minus 3x plus 1. Right? That's the function for which we want to evaluate the derivative. Okay? So define a routine that computes the function whose derivative we are interested in investigating. Okay? Perfect. Now, because I'm going to do the forward Euler on different values of h, I'm going to go ahead and create a Python routine that does that forward Euler for me on the fly. All right? So define forward Euler routine. So df, right, for df by dx, that's f prime. And again, like we did last time, so you see why I do these examples over time. We're spending a lot of time doing these little examples here, because next time we hit coding, we're going to pick up from where we left off. It's going to go faster. So this routine should work for any function f at any value x, and for any spacing h. And I simply return f of x plus h, f of x plus h minus f of x over h, right? Finally, I need the true value. I need the true value of f prime of x. Again, this is a toy problem to illustrate the concept. This is called verification, all right? So for x equals 0.5, the derivative, true derivative, is equal to 2x, right? So the derivative of x squared plus 3x plus 1 is 2x minus 3. So it's 2x minus 3 at x equals 0.5. Agreed? Okay, perfect. All good so far. And if you're like not trusting this, just print true derivative. Should give you a value. Okay, minus 2. Oh, cool. Okay, now let's declare all values for h. So we'll call this h vals, and we'll call it like last time, an NumPy array. And we had 0.1 and 1.01 e to the minus 2, right? 1.0 e to the minus 4, 1.0 e to the minus 6, 1.0 e to the minus 8. Don't do to the power minus 8. Python will treat it's very expensive to do that. Just do 1 e to the minus. 1.0 e to the minus 10 and 1.0 e to the minus 12. Okay? Perfect. So now my numerical derivatives is simply equal df. I'm going to call it on my function at the x value of 0.5, and for all h vals. Agreed? So to compute our approximation of the derivative for all of those values of h, I simply call df. I give it my function name. I give it the x value, and I give it an array of h values. And magically, it's going to compute that forward Euler approximation for all of those h values. Again, you don't trust this, print it out. Print numerical derivatives. Okay. 1 now, 1.9 now, 1 moment, etc. So it's getting closer and closer to 2, maybe. Okay. Well, let's visualize it. All right, so now we can define the true error. True error, which is the absolute value of the numerical derivatives minus the true derivative. Right? That's the true error. True value minus approximation. Okay? So let's go ahead and plot it. PLT dot. You can use a plot. you can just do plot. But for these cases, I know that a log-log plot is going to be better. And that's what the coding activity asked anyway. So you can start by doing a regular plot, plt.plot, and we will do h values. Remember, we're plotting the error versus the h values, if that wasn't clear. So I want to see how the error changes as h is changing. What is the expectation is that the true error decreases as h decreases. Agreed? That was what the truncation error told us, was less than 1 over 2 m times h. So as h approaches 0, so does the true error. Okay? Plot h, and I'm going to plot the true error. Okay? Okay, h values. Sorry, h vals. Just a straight line. Okay? So as h is decreasing, starting with 0.1, 0.8, 0.6, 0.6, etc., there's something off here, though. There's a little kink I can see. Let's try a log-log plot. But before I do a log-log plot, wisdom piece number 2. When you have discrete data that is limited in size, like 10 points, 5 points, 17 points, do not use a straight line. If you want to use a straight line, connect the dots. So for discrete data, always use symbols so that you know where your data points are, especially if they're sparse. Okay? Because you give the illusion that you have a continuous function. What Python is doing is just simply connecting a straight line between two consequent dots. But that might not be true. What if there's a curve between the two points? Okay? So my advice is that you just do this and do O. Okay, so now I have these points, but there's only 1, 2, 3. We should have more points. Well, the log is gonna fix that. So if you do, you don't even have to type anything. You just go a comma and then open this these single quotes and do O, and then if you do dash after it, it's going to connect them with a straight line. Now the next best thing is to do a log-log, because the log-log is going to separate all of those values apart from each other so you can see them better. And there's a little gem, little surprise that is going to show up over here. Oh. See that little kink I told you about? It grew up. Okay, so now I want to do one more trick, because it's a little confusing for me to read from right to left. Something is decreasing. I know h is decreasing in this direction. I want to flip the x-axis so that I go from left to right, top to bottom as I'm reading the plot. Again, these are tricks for better visualization. Yeah? Then I'm going to do plt dot. Okay, let me see how I did it in the. Okay, I'm going to change the limit, plt dot x limit. I'm going to go from the small value to the from the large value to the small value. So if I flip it, now I'm starting with small values of h and high values of h and decreasing. Okay, so let's start at the first point. If you're done coding, follow with me, because this is the important point here. Our hypothesis, our expectation was that as h is decreased, so does the true error. That's what the math was telling us. The truncation error was less than 1 over 2 m times h. M is a constant, so as h approaches 0, the error should approach 0. Okay, so that's what we see. We decrease h, the error is decreased. We decrease h, the error is decreased. We decrease h, the error is decreased. It's decreased, and then, what happens? The true error starts increasing. Yikes. What's going on? Don't look at the slides. If you looked at the slides, try to understand why I made that statement in the slides. What do you think is going on? So in our approximation of the derivative, we're crunching numbers, f of x plus h minus f of x. So there's an addition, there's a function evaluation, there's a subtraction, there's a division. What happens when you operate on numbers? What does the computer do? It incurs rounding errors. Exactly. And it just so happens, this magical example, there's a point, the true error is so small that round-off error is bigger than the actual truncation error. So in an ideal world, the math that I showed you, that doesn't account for round-off error. But the total error consists of that truncation error plus round-off. Every time you operate numerically on a computer, you incur round-off. So really, the total error is the mathematical truncation error plus the fact that we put things on computers. It just so happens in this case, initially, the true error was dominant, and the round-off error was so small, and then until we hit a point where the round-off error became larger than the truncation error, and it showed up over here. Okay? So that leads us to the concept of total numerical error. Okay? Total numerical error is simply the sum of a truncation error and round-off errors. Every time you have a numerical procedure, you're implementing on a computer, you have round-off error. If you have truncation, you add that on top of it. Okay? We know the bounds of the truncation error, which we showed mathematically, but you still have to worry about round-off errors. Okay? So what the previous plot actually tells me, and this is something we use in practice, is that there is an ideal value of h. So you can go and try to approximate a derivative, and you take h smaller and smaller and smaller. In fact, you're not getting any better, because round-off starts taking over. And you can see this in the Python numbers. Look at this. These are the results of the numerical derivative. The true derivative was minus 2. So the numerical derivative with the first h value starts at minus 1.9, then minus 1.99, minus 1.999. Then we get to minus 2.00, and then we lose it. It goes up, and then it just changes value, right? It gets farther from 2. It was getting closer to minus 2, and that gets farther away. So I wouldn't go. So there's a limit to what h values you can use. So next time you go and you say, I'm going to approximate my derivative, I'm going to use the smallest ever h value, well, you might be committing more error than actually using a larger value for h. Okay? Pretty interesting stuff. And with that, we'll close up the, let me see if there's like one more slide. Okay,